everybody. Welcome back to Mathematical Statistics. We have been talking about hypothesis testing, and yes, talking is the operative word. When I was editing my last video, it was just like blah, 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 get to the point. We didn't actually get to any examples of hypothesis testing, so I want to make sure we do here. And yeah, we're going to do a lot of examples, but first, a few reminders about where we are. So we have a random sample, presumably x1 through xn. Random sample means their IID independent and identically distributed. So their IID from some distribution with a parameter, and our generic parameter is called theta. And theta could be two-dimensional, so theta could represent lambda for an exponential distribution or mu for a normal distribution, or it might actually represent both mu and sigma squared for a normal distribution, or both alpha and beta for a gamma distribution. But for today, actually for all of this initial foray into hypothesis testing, because we're going to come back to it later in the semester after we have methods of estimation that are more formal than what we've been doing, we are just going to deal with one-dimensional parameters. So think of this theta as one-dimensional, and this has an associated parameter space, a place that it lives. For example, the mu for a normal distribution can be anywhere on the real line from minus infinity to infinity, and the lambda for an exponential can be a positive real anywhere from 0 to infinity. Whereas the parameter p for a Bernoulli distribution takes on values between 0 and 1 inclusive. So that's three examples of a parameter space. And we have hypotheses. We kind of want to know whether the parameter is in one part of the space versus the other. So first up, we have something known as a null hypothesis. This is denoted with an H0 or an HO. And this is a statement that says theta is in some subset of the parameter space. So suppose we are talking about theta being lambda for an exponential and the parameter space being the positive reals from 0 to infinity. This null hypothesis might say that lambda is actually on the interval from 1 to 3 inclusive. And then we get an alternative hypothesis, which fills out the rest of the parameter space. So the rest of the probabilities for the parameter. This is usually denoted with an H1 or an HA. That's okay too. And here we say theta is in the rest of the space. So this is going to be a complement of whatever this set is with respect to whatever the space is. Now, the null hypothesis is always assumed to be true in hypothesis testing. So you start with some baseline, you believe this is what's true, and then the alternative hypothesis is what you're out to show. And you always go with the null hypothesis as your conclusion unless your data strongly suggests otherwise. So your data has to convince you to go with the alternative hypothesis. Otherwise, you're staying with the null hypothesis. In hypothesis testing, you're going to make mistakes, and it has nothing to do with you or your abilities because you're going to see weird samples sometimes, extreme samples. So let me try to get just a little more specific. Suppose we are looking at something like, you know what, for most of today, we're going to start with simple versus simple hypotheses. Let me remind you what that means. So simple versus simple. A lot of people think that a simple hypothesis is something that has an equal sign, and that is part of it. So let me be more specific here. Suppose we're talking about x1 through xn, IID, normal, mu, free. A simple hypothesis is one that completely determines the distribution. Therefore, this hypothesis is simple because if you know it's true, then you know your data comes from a normal 3-3 distribution, and that's completely known to us. There's no unknown parameters. The same thing would be true if I put a sigma squared up here and I said where sigma squared is known. So kept it a little more generic, but saying that we know it, then this is a simple hypothesis. But this equal sign hypothesis would not be simple if that sigma squared was not known, because then we'd say, if this is true, we know the data comes from a normal distribution with mean 3 and some unknown variance. So I don't know exactly which normal distribution. So roughly speaking, a simple hypothesis has an equal sign, but that's not really true. Strictly speaking, it completely determines the distribution. If you know that hypothesis is true, you know exactly what distribution your data is coming from. So when I write simple versus simple here, I mean that we're going to start off by looking at a simple versus simple hypothesis. Now, this doesn't really go with what I was just saying. The null hypothesis should be that the parameter, in this case mu, is in some subset of the parameter space. In this case, the parameter space is the whole real line for minus infinity to infinity. And so if I have mu equals 3 here, I should really have this one being mu does not equal 3. I should fill out the entirety of the parameter space. But this is a simple building block example. So we're going to start here. And you should think of the parameter space being shrunk down to only include these two values. We are going to assume that this is true. And likely, in order to get a handle on mu from the sample, we're going to look at the sample mean x bar. So if the sample mean is 2 billion, not the right number of zeros, that's a lot of zeros, then neither of these look true to me, especially if this is our variance. We don't have a huge variance, but we're going to go with this one because it's better. It's closer to 3 billion than 3 is. And similarly, if x bar is negative 2 billion, we're going to stick with the null hypothesis, which we assume to be true from the beginning, even though it doesn't appear that either of these are true. So this is all the possibilities. And this is assumed to be true. And if we have evidence for this, we'll move to that as our conclusion, but otherwise we stick with this. And there is never any concluding something different than one of these two hypotheses. Okay, we had a table last time. It was a 2 by 2 table where we talked about the types of error you could make in hypothesis testing. So suppose this is our setup. We have a normal distribution with a known variance of 3. Um, then if you look at x bar to try to figure out where mu is, we do know that x bar has a normal distribution and its mean is the same as that of the original data, and its variance is the original variance over n. So if the null hypothesis is true, then this distribution is going to look like some kind of bell curve centered at 3. And I don't have any scale here. I don't know how big n is or how small this variance is. It could be a very spiky little skinny distribution if n is large. But even if the null hypothesis is true, x bar here takes on values all the way from minus infinity to infinity. So it's entirely possible to see x bar being 5 or greater than 5, even though the true mu is 3. And that's why there's going to be some error, because you're going to be comparing two distributions here. Like, does x bar come from the white distribution or the green distribution? They both have an entire support set in common, but the idea is going to be if our sample mean is greater than 3 significantly, so high enough, there's going to be some kind of cutoff point above 3 where we're going to make a decision and say, I don't think the mean was 3 anymore. I think it was 5. So that's what we're going to do today, and there will be mistakes. So recall that we had errors in hypothesis testing, which again has nothing to do with you or your abilities, but I made a 2 by 2 table with reality over here, and the reality is that the null hypothesis is true, and the other reality is that the null hypothesis is false. Then you make a decision. So over here, I'm going to put your decision. You either are sticking with the null hypothesis or rejecting it for the alternative. In the last class, I wrote here and here, accept the null hypothesis or reject it. I did that on purpose because it was our first time seeing it and I wanted a nice binary table. But you never accept a null hypothesis. You either reject it or you don't reject it. It's assumed to be true, and it's just like an idealized American court system, whether or not you think it's true or not. People are innocent until proven guilty. So you can think of the null hypothesis as innocence and the alternative as guilty. And so we're assuming this until we have evidence for this. And then at the end of that trial, you never say you are innocent. You say you are guilty or you are not guilty. So we never conclude, first of all, we never prove anything with our data, but we see evidence for not going with the null hypothesis. So we're going to reject it or not reject it. So I'm going to make my table a little better here. Your decision is going to be either to fail to reject the null hypothesis, in essence, accept the null hypothesis, but that's not the language we should use, versus our decision to reject the null hypothesis. So if it is true and we fail to reject it, we did good. We shouldn't reject it because it's true. And if it is false and we reject it, we also did good. We should reject a hypothesis that is false. And these other two boxes represent types of error. This one up here is known as a type 1 error. And this one down here is known as a type 2 error. So there is some probability of us making a type 1 error. If I go back to this example again, um, it could very well be that the mean is 3. And so we're looking at like this PDF here. And it's possible that the values sampled from this distribution are kind of on the high end and give us a large sample mean X bar. So we might end up rejecting this and going with this, even though we shouldn't. So that's a type 1 error. And what you do as a statistician is you have the scientist that you're doing the test for give you their idea of what kind of risk they're willing to accept, what kind of error they're willing to accept. Of course, we would like 0 error, but that's not going to be possible because, well, you'll see. But there's going to be a trade-off between these types of error. So the probability of making this type 1 error, I'm about to give that a name, is has an inverse relationship with the probability of making a type 2 error, but it is not a 1 minus relationship. We will see that in some cases, but that's just special cases of hypotheses and distributions we're working with. The reason they don't have a 1 minus relationship is because we are stuck in one of two universes. This is one universe, and the second row is another universe. So the probability of making this type 1 error is 1 minus the probability of not making the type 1 error. Again, there is not a 1 minus relationship between these two types of error. Okay, so I want to define these probabilities. We have names for them, and this is only going to be a definition in the simple versus simple case. So let me just start off by saying for simple versus simple hypotheses, we can talk about the probability of making a type 1 error. And this is known as the level of significance of the test or something else. Let me get this down here. The level of significance of the test, or we can talk about the size of a test. These both mean the same thing. Level of significance tends to be used in a more data-oriented environment or course, if you're taking a statistics course, and size in a more theoretical environment like mathematical statistics. So I'm going to use size more for reasons that will eventually become apparent. Right now, it would be hard to explain until we see what's happening and what it represents the size of. But these are two terms for the same thing. So it's denoted and defined universally denoted by an alpha, and this is the probability of making a type 1 error. So this is the probability of rejecting the null hypothesis when you shouldn't because it's true. And you should say it in that order. You shouldn't say the probability it's true and you reject it because it is either true or false. That's not where the probability is. The probability and the chance of us making a mistake comes in from us actually saying, I'm going to reject it or fail to reject it. The level of significance or size of a test is specified in advance for the person that actually cares about the underlying scientific problem. And there is, of course, the type 2 error. So this one doesn't really have a name, but it's associated with something that does have a name. So a beta is used to denote the probability of making a type 2 error. I want to emphasize again that these definitions are for the simple versus simple cases, and you'll see why we need another definition, which will be equivalent to this when we move to composite hypotheses. So the type 2 error says, in the case that the null hypothesis is false, you failed to reject it. So this is the probability you fail to reject the null hypothesis when you should have because it is false. So beta does not really have a name, but if you look at 1 minus beta, this is important to people because we are stuck in the universe where it's false. But 1 minus beta is the complement, it's the probability of the complement of this event. So staying in that universe where it's false, this represents the probability we not fail to reject, but do reject the null hypothesis when it's false. That's a good thing. If it's false, you definitely want to reject it. And this quantity is known as the power of the test. And so it's going to be a goal to have a test with high power, which is equivalent to having a low probability of a type 2 error. And as we move on towards the end of the semester, when we do more advanced hypothesis testing, we are going to figure out what the most powerful possible test is for certain sets of hypotheses. And if that doesn't make sense, let me do some examples today where we want to test some things, and I'll come up with two different tests and we can talk about comparing them and which one is more powerful and whether or not there's a third test that's even more powerful or one that is most powerful. I think that's enough for us to get going. So for my first example, I'm going to keep this one very concrete with lots of numbers. Suppose I have x1 through x10. I mean, if I'm using numbers, I'm using numbers everywhere. So n is 10. IID from a normal distribution with mean mu and a known variance, and I'm going to make it look really known, 3. I want to derive a test of size or level of significance alpha for this set of hypotheses. I'm going to say either mu is 3, which is assumed to be true, and we're going to look for evidence that the mean is really 5 or at least greater than 3. So it's more likely to be the 5 than the 3. Part of what we do in here is to figure out, like, we're going to work with some statistic, and what statistic should you work with? So you're going to take some function of the data and work with that to come up with your result here. Because it is a test involving a mean, we'll probably use a sample mean. In this part of the course, this part of hypothesis testing, I will always say this: based on and I'll give you a statistic. But in a later part of the course, when we come back to hypothesis testing, you're going to have to choose a statistic and choose it wisely to get the best test. So we're going to go through the motions now, assuming the statistic has been chosen for us. Okay, instead of deriving a test, well, suppose someone did it and they came up with a final rule for rejecting the null hypothesis. And this rule that I'm completely making up, so don't worry if you can't see where it came from, it doesn't come from anywhere, is going to be to reject the null hypothesis. And then I do need to say in favor of the alternative, especially in a case like this, where I do not have the whole parameter space covered. Um, if my sample mean X bar turns out to be negative 3 billion, I am going with the null hypothesis. And if it is, we're only going to be able to reject it in favor of the alternative. It might actually not look true at all given your sample mean. I didn't say that very well, but this should become clear soon. So I'm going to say that this rule is we're going to reject it if we look at X bar and X bar is greater than 4.5. Where did that come from? Totally made up at this point. Our job is going to be to figure out what this number should be in order for us to get the correct or desired probabilities of making type 1 and type 2 errors. But suppose this has been given as our quote unquote rejection rule. Let's look at the size or level of significance of this test. We're calling it alpha. This is the probability of making a type 1 error. This is the probability you reject. Remember the 2 by 2 table. You reject the null hypothesis when you shouldn't because it's true. Now, for us, our rejection rule says that rejecting the null hypothesis, that's going to happen when X bar is greater than 4.5. And when it's true means when the mean is 3, because that was the statement of the null hypothesis. Let's compute this probability. We are under the assumption that we come from a normal distribution and there's 10, n is 10. So if the mean is 3, this tells us that x1 through x10 is IID normal 3, 3. And those are the numbers we should work with when trying to standardize this and turn it into a standard normal, which is what we always do for computing probabilities for normal random variables. I'm just gonna, in the corner down here, say that you want to standardize this variable by subtracting its mean and dividing by its standard deviation. But because the mean of X bar is the same as the mean of the original X's, and because the variance for X bar is the original variance over N, we're going to get a more specific form over here. I'm going to subtract the mean mu and divide by sigma over the square root of N. And as usual, on the variable side, I'm going to keep it symbolic. And then on the other side, I'm going to keep it numeric. So 4.5 minus 3, because we are under the assumption that that is the mean. And then divided by sigma. So here, 3 is sigma squared. So this is going to be the square root of 3 over the square root of n, which is 10. And yes, you certainly can put one big square root on everything in that denominator. I shouldn't have closed the parentheses. I do need to keep saying when mu is 3, because that's really relevant for the next step. We do know we started with a normal distribution, so we know this is normal. And here we kind of standardized it into a standard normal. Except we didn't if this mu is not 3. If the true mean is 5 and we subtracted 3, then it is not something that is now centered at 0. It is not a normal 0, 1. So this piece of information allows us to say that this first term here is a standard normal. Let me put that over here, where z is normal 0, 1. 0, 1. And this other term is whatever it is. Looks like 2.74 and more digits, but because I'm going to go to a z table, I really only care about those first two digits. And now I don't need to continue writing when mu equals 3 because that information has been used up kind of. To compute this probability, we use this distribution and it doesn't depend on a 3 or something. That's already been taken care of and kind of wrapped into this. So we're trying to find this alpha. We rewrote it as this probability, and we know how to find this using a z table, or maybe you're finding this using software. Our table, we had CDF or cumulative values like less than or equal to probabilities. So I would write this as 1 minus the probability that z is less than or equal to 2.74, and then go to the table. So I'm not going to go to the table here. I'm just going to, I'm not going to scroll back and forth, but I'm looking at a table. This looks like it's 0.9969. So make sure you can get that number either by software or the table. We're not really going to need it in here because this is an example with real numbers, but for the most part, things are going to stay symbolic and look like critical values like z sub alpha. But this is 0.0031. So that's our alpha. That's the size or level of significance of the test, which is the probability of us making that type 1 error where we reject the null hypothesis, but we shouldn't because it's true. Okay, let's look at beta. Beta is the probability of making a type 2 error when using this decision rule, this rejection rule. We're going to reject the null hypothesis in favor of the alternative if we see that the sample mean x bar is greater than 4.5. So remember, this is the probability we fail to reject the null hypothesis when we should because it's false. If we reject when x bar is greater than 4.5, then we're going to fail to reject if x bar is less than or equal to 4.5. And the when it's false means that mu is actually 5. We had two hypotheses. Mu is 3 versus mu is 5. And the 5 was the alternative hypothesis. So now we do the same sort of thing. If the true mean is 5, then x1 through x10 are IID, normal, 5, 3. And going back over here, I'm going to subtract the mean and divide by the original standard deviation over the square root of n, and then I'm going to do it numerically on the right side. So I'm going to subtract the mean of 5, and the variance was 3, so the square root of that, square root of 3, square root of 10, when mu is 5. We do know for sure that this is normal because we started with the assumption that we had data from a normal distribution. And now we have standardized it to recenter it and rescale it. And if the true mean is 5, then we have recentered it correctly, and we get a standard normal random variable that we can call z. And then this number is negative 0.91. And I no longer need to carry this around. I did use this in order to conclude this. Kind of those pieces of information went together. But the z has a standard normal distribution. And this does not depend on knowing what mu is. So I don't care that mu is 5 at this point. Right. So if you are trying to go to your table, you have a 0 here and like a negative 0.91 here, and you want a probability like this, which by symmetry is the same as the probability of being above zero 0.9, but our table gives us less than probabilities. So this stuff up in the right tail is 1 minus everything below it. So this is 1 minus the probability that z is less than or equal to positive 0.91. And you can go to your table and get that. And I encourage you to do that just to make sure you can find these things. And this turns out to be 0.1814. So that's our beta. That's our probability of making a type 2 error. We have the power of the test is 1 minus beta, which is 1 minus 0.1814, which is a number, and hopefully it's a larger number rather than a smaller number, and it is. It's going to be zero point 0.8 something. So that's kind of large relative to some things here. But this is the result for the alpha, the beta, and the 1 minus beta. When someone gives you that rejection rule where they came up with this number, 4.5, as a cutoff for when things are getting too large. However, as mentioned before, the probability of making a type 1 and type 2 error need to be specified by the domain expert, the person that's actually, the biologist who's asking you to determine something with a hypothesis test for them, or the geologist, or the ad executive, or anyone who's asking you to to test something for them in their field. They're going to give you their tolerance for error, and the most used or usual values for the size or level of significance of the test are 0.05, zero point 0.01, zero point 0.1. But in this class, I'm going to make sure to give you some really weird ones like 0.27 or something like that, just to make sure you know what you're doing and aren't relying on the fact that you see these numbers over and over again, and so you know what the cutoff should be. So, but these are the most common values. The beta is not talked about nearly as much, and that's because it's often locked in. You often can't set the beta. It's possible, but I need to do a different example first to show you when that would be the case. So let's do this example. Let's continue the example we're in. So I've got like, here, I'll call this a new example. I've got x1 out through x10, IID, normal, mu 3. The null hypothesis is going to be that mu equals 3. The alternative is going to be that mu equals 5. And those are all the possibilities you get to work with. So we've kind of narrowed down the parameter space, and I repeat myself all the time as the teacher in me, but if you if it seems to you like the mu is negative 40 billion, you're going to go with this one instead of this one, but you're not going to draw a different conclusion. So last time, and just above in this example, I said the rule for rejecting the null hypothesis in favor of the alternative is going to be to look at x bar and to reject the null hypothesis if x bar is greater than 4.5. Here, I want to figure out what that number is, so let's derive a hypothesis test of size or level of significance. Alpha equals 0.05 for these hypotheses, in this case of normality, based on the sample mean x bar. So after this example, I'm going to write things out in a series of steps. There's, to me, 4 steps. Some people think it's 3 steps. Some people think it's 5 steps, whatever. Right now, it's a little more freeform. But if we assume this is true, and we're looking at the sample mean, what do we need to happen in order for us to conclude this is true? We need the sample mean to be greater than 3 and significantly greater than 3, whatever that means. Maybe not greater than 4.5. Maybe it needs to be greater than 6 before we say it's really greater than 3. Because the sample mean is a number computed from data, and it's a relatively small sample. So if you grab a sample of size 10 and compute x bar, and I grab a sample of size 10 and compute x bar, we could get some pretty wildly different things, because x bar can go everywhere from minus infinity to infinity. So how far above 3 does this need to be before we go with the alternative hypothesis? I don't actually care about how far it is above 3, although I could frame my solution that way. I really care about just saying it's large enough, right? So the idea or the form of the test is going to be something like, let's reject the null hypothesis in favor of the alternative if X bar, which we're supposed to be basing this on, that's been given, is in some region. So I'm going to say is greater than a constant C for C to be determined. Is the C 4.5 or is it something else? Right now, we're letting the experts give us the probability of making a type 1 error. We decided to go with 0.05. So we're going to kind of reverse engineer what we just did to figure out the cutoff that will give us that as the type 1 error probability. Let's do it. 0.05 is the probability of making a type 1 error. This is the probability that we reject the null hypothesis, but we shouldn't because it's true. And rejection for us is this rule, X bar is greater than C, even though we don't know what that is yet. And when it's true, means that mu is 3. How do you compute a probability involving a normal? When mu is 3, we know that x1 through x10 are IID, normal 3, 3. So we know how to standardize X bar. We're going to subtract its mean, which is the same as the original mean for the original data, and we're going to divide by its standard deviation, which is sigma over the square root of n. And then on the right side, I'm going to do this numerically. So C minus 3 over the square root of 3 over the square root of 10 when mu is 3. And if mu is 3, that tells us that this is standard normal. We can write this as the probability that z is greater than c minus 3 over the square root of 3, square root of 10. And I don't need to carry this around anymore, but I do need to say where z is normal 0, 1. And because this doesn't depend on knowing what mu is at this point, I've used up that information, so I'm going to stop dragging along the when mu equals 3, when mu equals 3, etc. Okay, as a reminder up here, this is equal to 0.05. So let me kind of recap that here. We have 0.05 is equal to the probability that a standard normal is greater than c minus 3 over the square root of 3 over the square root of 10. And so let's look at the standard normal PDF. We want to find a number that we are above with area 0.05 and below with area or probability 0.95. So what is this? To find this number, you would go to the z table. You would say, okay, well, what number am I below with probability 0.95? And I'll, I'll do one of these today. Let's go to our z table. So I'm looking for the 0.95 in the body of the table, and it appears to be right between these two numbers. It's actually exactly between those numbers. If it was closer to one than the other, I would go with the closer one. I don't think interpolating between the values is really worth it. But because it's just in the middle, I'm going to go with, so the number 1.64 captures area 0.9495 to the left, and 1.65 captures area 0.9505 to the left. So let's go between 1.64 and 1.65, only because there isn't a closer number here. They're both equally spaced away from 0.95. And so I'm going to use 1.645. So this question mark is 1.645. And if you are using software, you can get a more exact critical value, but people all over the world use these kinds of numbers in statistics. You're going to see a lot of 1.96s and a lot of 1.645s. So this is the number that the standard normal is above with probability 0.05. And this means that this has to equal that number. So c minus 3 over the square root of 3 over the square root of 10 is going to be 1.645. And so if we go through and solve for C, then I'm going to have to multiply that square root stuff over to the right-hand side. Please tell me I wrote this down. Yeah, so this, no, give me a sec. Okay, so this is 3.90. So that, when we're testing these hypotheses, that's how far above 3 we need to be before we start thinking that the true mean is 5, if we want the size or level of significance of the test to be 0.05. And so we now have a rule here. So the final conclusion for our hypothesis test is going to be reject the null hypothesis in favor of the alternative if x bar is greater than 3.9. Someone gave us the alpha, and that helped us find the cutoff to get that alpha. Let's look at the probability of a type 2 error. I didn't give you what this should be, and that's because we really can't control this for this example. It is already locked in. The type 2 error is when you fail to reject the null hypothesis, but you should have because it's false. Our rejection rule is right up here. We're going to reject when x bar is greater than 3.9. So we're going to not reject if we look at x bar and it is less than or equal to 3.9. And when it's false, means that mu is the alternative value of 5. This is a fixed number. If the mean is 5, then x1 through x10 are IID normal 5, 3. And going back to the left side, if I look at x bar minus the mean mu over sigma over the square root of n, this is less than or equal to 3.9 minus 5 over the square root of 3 over the square root of 10 when mu is 5. And if the true mean is 5, and we did this, then we did center it to 0, which means we get to call the thing all the way on the left z. Then on the right, I think we get negative 2.01. And I no longer need that mu is 5. I just now know that z is from a distribution with all the parameters known. And I'm not going to go to the table for this. If you look this up, this is 1 minus 0.9778, which turns out to be 0.0222. So that is the beta, which means we can compute the power of the test, which I actually don't care about. We're going to talk about that more on its own later. But this test has high power because 1 minus this is a relatively large number. But it is fixed. So the domain expert, the person we were deriving a test for, said, I'm willing to accept probability 0.05 of making a type 1 error. And that led us to a rejection rule. But that rejection rule already has beta locked in, so they couldn't also tell us what beta they wanted. And the reason is there aren't enough things unknown here. So if you wanted to kind of pre-specify both alpha and beta, then you would need to have another unknown. You would say, like, I'm going to reject if x bar is large, but there's this one unknown. And maybe you would have to free up the sample size. So to have another unknown. And then your rule, if someone gave you an alpha and beta, would be you need to take a sample of this size, of size 16, and reject if x bar is greater than 3.9 to get your alpha and beta. And I totally made up that 16, so that's just not going to work. So beta is locked in for most of our problems unless we free up another parameter of the problem. But we had the n known, we had the sigma squared known. We just had one unknown, and that was the mean mu. And yeah, so we could specify an alpha, but we couldn't specify a beta, although there's nothing saying we couldn't do that in reverse, but people tend to not do that. But someone could give us the beta they want for their test, and we can just kind of redo this problem in a beta-centric way and then our alpha would be locked in. Okay, that is way too many numbers. That is way too much in terms of numbers for this course. So let me do one more of the same example, but much more generically. Suppose I have x1 out through xn, so I don't have x10 but xn. They are IID from a normal distribution with mean mu and variance sigma squared, where sigma squared is known. So it's like having the 3 in there, but it's not, I don't know what it is, but it's known to us. And I want to derive a test of size or level of significance alpha for the null hypothesis that mu equals something versus the alternative that mu equals something else, because we are still in this simplified setting of simple versus simple hypotheses. Before I had a 3 versus 5 here. Now I want to put more generic numbers. So we usually say something like mu naught and mu 1, and those are known numbers. But as we saw, it is important to us to know which one is smaller or larger to figure out the kind of form of the test. Like if this is larger than this one, then we're going to kind of go with the alternative hypothesis if x bar is large. If it's the other way around, we're going to switch that up. So these numbers are known to you. The sigma squared is a fixed number, the n is a fixed number, mu naught and mu 1 are fixed numbers, and therefore they have an order which we can look at and see. But because I'm writing it generically, let's assume it's like the other problem. Let's assume that mu naught is less than mu 1. Okay, I didn't finish this phrase, derive a test of size alpha for this. This is just a side note. And based on the sample mean x bar. So it's the same problem, but everything is going to look more general. And this is how all of our problems are going to look from now on out. And there are, in my opinion, 4 steps to hypothesis testing. Step 1 is going to be to choose a statistic. Usually, this is not going to be given to you. So someone's going to say, derive a test for me. And you'll probably say, this test is a test for the mean mu, so I'm going to look at the sample mean. But you could look at the maximum minus the minimum, which is called the sample range. Just like with confidence intervals, you can use almost anything as long as you can work with it. And given several options that you can work with, some are better than others. But the first step is going to be to choose a statistic, and that's been given here. It's done. We're going to use X bar. Step 2 is to write down the form of the test. We are assuming that the null hypothesis is true, and we're going to look at X bar to maybe not go with that and go with the alternative. In this example, this alternative hypothesis is the larger of the 2 numbers. So you have to ask yourself, how does that reflect in this statistic? If the true mean is really mu 1 versus mu naught, and mu 1 is larger, X bar is going to end up larger. So the form of the test is going to be to reject the null hypothesis in favor of the alternative if X bar is large in some sense. So let's say X bar is greater than a constant C, or C to be determined. And this was entirely determined, this form, by looking at the alternative hypothesis and how that would affect the statistic we're looking at, because there is a greater or larger number here, and that turned into a greater than or equal to a number here. But it's possible for a different statistic or a different parameter that when this number gets larger, the statistic you chose gets smaller. So you don't just want to say there's less than or equal to here, and therefore this is a greater than or equal to. You really want to think about how the alternative hypothesis being true is expressed by the statistic. Okay, step 3 is going to be to find C. And here is where you use alpha. Alpha is the probability of making a type 1 error. This is the probability we reject the null hypothesis, but we shouldn't have because it was true. This is the probability, so rejection for us takes this form. Probability that x bar is greater than C when it's true means that mu equals mu naught. And we'll often write this in shorthand by saying, I'm not going to do it yet, but just so you or start to get used to it, I'm going to put a semicolon mu naught here, which is going to represent this whole little phrase. How do we deal with this probability? The x bar has a normal distribution. And if mu equals mu naught, this tells me that x1 through xn is IID normal mu naught sigma squared. And the n and the mu naught and the sigma squared are all known to us. So let's standardize our x bar. Going to subtract the mean and divide by the standard deviation. But numerically, we're assuming the mean is mu naught. The standard deviation is whatever, it's the square root of sigma squared. And yeah, these are known to us, but we don't actually have the numbers to do the arithmetic. And I forgot to write when mu equals mu naught. So let's use that piece of information again. If mu is mu naught, then this has been properly centered around 0. We subtracted mu naught, and that was the right thing to subtract. And that means we get to say this is a random variable z greater than this quantity over here, where z has a standard normal distribution. And this whole thing started with an alpha. So I get alpha is this probability. And let's look at the standard normal distribution, centered at 0 with variance 1. I want to be above a number with probability alpha, so below with probability 1 minus alpha. And our name for this critical value is little lowercase z sub alpha. Some people would call it lowercase z sub 1 minus alpha, so be careful when reading other resources. But this just tells me that c minus mu naught over sigma over the square root of n equals z sub lowercase alpha, which gives us c as mu naught plus z sub alpha sigma over the square root of n. And now we have step 4, which is to bring it all together and announce your conclusion. So we're going to reject the null hypothesis in favor of the alternative hypothesis if x bar is greater than c, but we just figured out what that needs to be. If x bar is greater than mu naught plus z sub alpha sigma over the square root of n. And we're done with this hypothesis test. We have derived a test of size or level of significance alpha for the given hypotheses and the given distribution um, based on x bar. We can do a type 2 error calculation here for beta. I don't think I'm going to do it. We're not going to get a number in the end, but it should be a function of the CDF for z. So remember, we had a name, we had a capital phi of little z is our name for the standard normal CDF. And so if you want to write out beta, it's going to be in terms of this, and I will do examples of that, but just not in this example. I want to get on to something else, but we will get to do many examples of that. As a new example, suppose I have x1 out through xn, IID normal mu sigma squared. Sigma squared is unknown, and mu is also unknown. I guess I could say that, but if it's a hypothesis test concerning mu, then it's going to be unknown. And let's derive a test of size alpha for, let's start looking at some composite hypotheses. I'm going to keep the null hypothesis simple. So mu equals a mu naught versus an alternative hypothesis that says that maybe mu is greater than mu naught, getting closer to something realistic based on the sample mean x bar. Step one is to choose a statistic. Write this up here. And we're done with that because it's been given for us. So we're using x bar. Step two is to write down the form of the test. So we've got that we're assuming that mu equals a number, say 3, and we're out to find evidence that mu is actually greater than 3. And that is going to be reflected in x bar by x bar coming out larger. If the true mean is greater than 3, that x bar is likely to be larger than it would otherwise. So this tells us that we want to reject null hypothesis in favor of the alternative because for our example, it's still somewhat simplified. There is no concluding that mu is less than mu naught. Uh, if x bar is large, i.e., x bar is greater than c for some constant c to be determined. Step 3 is going to be to find c. Now, neither of these hypotheses are simple. The alternative is definitely not simple because of the inequality, and the null hypothesis is also not simple because if you know that the true mean is that fixed mu naught, you still don't know entirely what this distribution is because sigma squared is unknown. So we're going to have to use the sample variance. And if we try to standardize a normal random variable here using the sample variance, if the sample size is large, then we can say it's all approximately good and we're getting a normal 0, 1. But if the sample size is small, then that's where the t-distribution comes in. So I might have been a little more leading and say where n is small, but really anytime you're using s squared instead of sigma squared, it's a t-distribution. It's just that in practice, people don't use the t-distribution when they have a sample size greater than 30 or so, because it all turns out approximately the same. But yeah, I'm not going to assume n is large. I'm not going to say it's small either. But what is going to happen here? So we are going to use alpha to find c. This is the probability of making a type 1 error. This is the probability you reject the null hypothesis when you shouldn't because it's true. Our rejection rule looks like this. So this is going to be the probability that x bar is greater than c when the true mean is mu naught. And I want to turn this into a standard normal, but I can't because the next step would be to say x bar minus mu naught, oh, well, actually mu over sigma over the square root of n is greater than c minus mu naught over sigma over the square root of n. We are always assuming our sample sizes are known in this course unless explicitly stated otherwise. But if you call this z, then you have something that you can't work with over here because you don't know sigma. So I'm actually out of time, but what we're going to do is try to standardize it using the sample variance. We're going to look at x bar minus mu over s over the square root of n, and use the fact that starting with our normal distribution, this has a t-distribution with n minus 1 degrees of freedom. So we're going to find the cutoff we need based on a t-distribution and t critical values. And we'll also get to see next time how this inequality really affects what's going on here. Um, because the type 1 error probability is going to work the same as it always has, but we're going to have a problem if we want to look at the probability of making a type 2 error, which you'll see hopefully next time. Please come back on mathematical statistics.